Okay, now a few things about the exam. I am going to let you have all the material available, but that does not necessarily mean that you are expected to read them, because you are not going to have enough time. In other words, that you will have enough time, but reading each paper is not going to make any sense during the exam, because you're going to have probably 2 hours for the exam. So given this, I would still let you have those there, because you might have some question marks that you may want to resolve in a few minutes. So for the papers to be there is very meaningful in that respect. Please don't bring anything else, but only the required papers will be sufficient, not even the recommended ones. I don't want you to bring the whole thing to the exam. And the questions that I'm planning to ask would be from the papers. This is going to be probably like half of the questions will be from the papers, and half I will try to ask some problems like homework problems. Okay, so this is what I'm thinking. The questions are not prepared, so it means that it can change, but I'll let you know. I'll put an explanation at the web before the exam. Okay? Now, regarding your homeworks, I am going to grade them probably weekend, and they will be available on Monday. But I looked at them. I don't think that there is like a very serious problem, but for the second homework, still I have to check that. Okay, and what else? I think that will be all. Tuesday morning, we are not going to have any lectures. So you are going to have an exam on the evening of Tuesday, and Thursday we are not going to have any lectures. So next week will be off so that you have time to do your homeworks. So it means that I'm going to increase the percentage of the homework. Well, that's fair. Okay. Now, one issue that we couldn't resolve last time was regarding the demand distribution. If you recall the variance of demand and so on. I don't know why, but I think sometimes it happens. It is in front of your eyes, but you don't see it. So the answers are actually very simple. I made a mistake. There is no typo in the book, but I made a mistake conceptually. So remember, the demand that Lee was using was something like this. And UTs were normally distributed with mean 0 and variance sigma squared. This is the process. Now you can see that the UTs are independent and identically distributed over time. So what I would expect would be the demands, the variance of demands. Now note that demands have a covariance. Now first let's find that. What is the covariance of dt minus 1? The covariance is simply, there is a row here, I'm sorry. Okay. So this is simply going to be, how are we going to compute this covariance? Well, we can use the definition, but you can see that the covariance term is going to be it's going to be the variance of dt times variance of dt minus 1 times rho. So this is actually the covariance of this term. Now, why is this true? Because UTs are independent. Okay, so UTs are going to cancel. So when you take the covariance of dt and dt minus 1, you're going to have the variance of the individuals. Okay, and then you're going to have the correlation coefficient coming in. Okay. Now, how about what is the variance of dt? Now, when you look at this process carefully, you see that the process is non-stationary, but the variance of demands are still going to be the same. Why? Because ut, the error term, regardless the size of the demand and the correlation, is the same and independent. So given this, then the variance of d is going to be simply identical irrespective of time. Note that they are going to have some covariance, but the variance is going to be identical. So what happens? How am I going to find that? Take the variance of both sides. So I will have variance of dt is equal to, variance of a constant is 0. Then I'm going to have rho square, variance of dt minus 1, plus, what is the variance of ut? It is sigma square. Now note that ut is independent of the demands. Okay? In other words, these two are independent, so when you take the variance, you can simply write the covariance term of dt minus 1 and ut equal to 0. Note that ut depends on dt, of course, but ut is independent of dt minus 1. So once you do that, and noticing that these variances are equal, okay, then what we have is variance of dt in general is going to be sigma squared divided by 1 minus rho squared. Okay, so the rho square comes actually from taking the variance of this term. So it was very straightforward, but in a way, I usually use my intuition, but one shouldn't use the intuition too frequently. Okay, so that was a mistake. Okay, so this is the variance term. So once we have the variance term, next thing is to compute the variance of, remember we had d0 minus d0, d minus 1. So you take the difference. Now, in order to take the variance, the best thing to do is to write d0 in terms of d minus 1. So what we have here is we have d plus rho d minus 1 plus u0 minus d minus 1. Okay? So this is the term that we want to take the variance of. So once we do that, then we are going to have the variance of d is constant. So we're going to have rho minus 1, or we can put it over there, u0 minus actually rho 1 minus rho d minus 1. So if you take the variance of this term, then you are going to note that these are independent again. So what we are going to have will be simply, well, there is a simpler way of doing it actually. This is one way, but just using this term, the variance of d0, d minus 1 is equal to variance of d0 plus variance of d minus 1 minus 2 covariance d0, d minus 1. Actually, this is the term. If you rewrite these, this is going to be sigma square minus 1 minus rho square plus sigma square divided by 1 minus rho square minus 2. Then I have the covariance term coming into the picture, which is sigma square divided by 1 minus rho squared. Why? Because in the covariance term, actually, what you have is, well, actually, these should be standard deviations. I'm sorry. Okay. So what you have is you have sigma squared divided by 1 minus rho squared to the square root times for the other one. So I have the same term times rho. So if you look at this, you're going to see that this is sigma squared divided by 1 minus rho squared is common. And then I'm going to have 1 minus 2 rho. Where is that? No, I'm going to have 2 here, I'm sorry, and 1 minus rho here. Note that I can write this as 1 minus rho, 1 plus rho. So 1 minus rho's are going to cancel, so I'm going to be left with 2 rho squared divided by 1 plus rho, which is the result actually in the text. Okay, so you can do the other thing in the same way. Okay, note that writing this becomes easy once you notice that this is the covariance term. Okay. Now, again, what was the bottom line of the paper? Let us remember that bottom line. Bottom line was if you have a demand process like this, which is known to be non-stationary, but non-stationary demand processes are not necessarily going to require non-stationary standard deviations. Here, in this case, the standard deviation is stationary. And this is actually what you're going to get regarding the process itself. Okay. Okay, any questions on this now? I think it is set. Sorry for the confusion. It happens sometimes. Okay. Now, last time, I think I started to do some work on the ordering problem. Am I right? I defined the problem. But let me go over it again. And I will now do that part in a little bit more detail. Okay, so again, we are dealing with information distortion. Okay, and what we are going to see is the effect of order batching in information distortion. So what we have is, if you recall, we are going to have, we have a system where we have n retailers. And we are going to have an order up to policy where this is the periodic review cycle. In other words, each retailer is going to order once every R periods. So this is set as well. And also, each retailer has a demand which is going to be denoted by XJT. So this is the retailer demand, retailer J's demand at time T is going to be normally distributed with mean M and variance sigma square. So I am making life a little bit easy. I am simply taking all the retailers identical. Okay. Now, question here is, these retailers are ordering, and then you have a supplier. So this is the system. Supplier is going to satisfy the demand for the retailers. Now, as they have an order up to policy and they order once every R periods, what does it mean? It means that they are only going to order the demand in the previous R periods every time that they order. Okay, so they are going to bring themselves to the same level. Let us assume that lead time is negligible and we are not going to be concerned with that. Because we know that if we are concerned with lead time, we are going to have an additional term in the bullwhip effect. Because lead time creates some bullwhip effect. So let us assume that lead time is 0. Now, given this, we are going to have 3 different types of possibilities with respect to the retailer's ordering. Now, what do we know? We know that a retailer is ordering once in every R periods. So we have 1, 2, 3, and this is R. So this is the time span in which the retailer is ordering. You can say that this is the, let's say this is a week, so we have 7 days. So some retailers are going to order on Tuesday. Some retailers are going to order on, let's say, Friday. Some retailers are going to order on Wednesday, so on and so forth. So given the retailer's ordering pattern, we are going to compute different bullwhip effects. Now, we are going to see 3 different behaviors here. Now, the first behavior, which is going to be, let's say, number 1, will be random ordering. So we are not going to have anything in our mind, but we will simply let the retailers select the time that they are going to order randomly. But once they select that, they are going to keep up with that, of course. Okay, so this is more or less the idea. Well, as long as it is random, actually, it doesn't matter because they can change it every period, every cycle. But as everybody is random, it's not going to change anything. And they are all identical, of course. Okay, so what we are going to do is, now under random ordering, we are going to write the variance of orders and compare it with the variance of demand. Of course, we are going to do that from the perspective of the supplier. So supplier is going to see all that demand coming in, and this is the variance that we will be interested with respect to the variance of demand. And then the supplier is going to receive orders. We are going to look at the variance of the orders that the supplier receives and compare. Okay, so in order to understand, in order to pursue this, let me define a random variable. Let n be a random variable denoting the number of retailers who order in a randomly chosen period. So n is going to be a binomial distributed random variable. So what does this mean? I am looking at the total number which is going to select a certain day. So n is going to be each retailer's contribution to that day is actually a Bernoulli distribution. A retailer can include herself or exclude herself from that day randomly. So it is basically, you see that it's a Bernoulli distribution. So when you count the sum of Bernoullis, it is going to be binomial. So what are the parameters of the binomial? The population is limited. How many retailers do we have? Capital N. So n is going to be the first parameter of the binomial. And what is the probability that a retailer is going to include herself in a given day? We have R days. It is random. So we are going to assume uniformly distributed, of course. So this is going to be 1 over R. So any day can be selected randomly. So we have R days. So probability of selecting any day will be 1 over R. Now you can immediately see the second case. We are going to make sure that in the second case they order all at the same time. Why? Because, for example, if we're talking about the retail environment, it is reasonable for them to order on Thursdays, okay, rather than somebody ordering on Sunday. Why? Because Friday, Saturday, Sunday are the times where you have the peak demand. You usually want to order before the peak demand comes. Otherwise, you're going to carry a lot of inventory. Okay? So this is more or less the idea. So, but here, this is random. So n is going to be binomial with capital N and 1 over R. Any questions on this? Okay, so now we can find the expected value of n. The expected value of n is simply capital N divided by R, which is very logical if you have 35 retailers, okay, in total, okay, and if R is, let's say, 5, so on the average you expect 7 retailers to give an order in a given day. Okay, so this is reasonable, and this is going to be the same for all cases, of course. Now, how about variance of n? Variance of n is variance of the binomial distribution, if you recall. Variance of the binomial distribution is n times the probability, 1 over R, times 1 minus p, if you recall. This is 1 minus 1 divided by r. So this is the variance. Okay. Any questions on this? Okay. Now, next step will be, of course, to define the quantity which is ordered. So let z sub t, now I'm going to put a superscript ran, which denotes random. So z is defined as the quantity total orders from n retailers, çok yaşa, in period t. And of course, t is going to change from 1 to r. And of course, this z is a random variable. Okay? So now what I am after is, I am after the total quantity which is ordered under this scheme. Okay, so how am I going to write the quantity ordered? Of course, n is a random variable as well. So I have two random variables here embedded. One of them is n, the total number of retailers that give. The other one is the quantity that they order. So, but still, I can write zt ran as the summation. I'm going to have two summation, j from 1 to n, where this n is a random number. Okay, and then for each retailer that orders, I'm going to simply sum the demand from t minus r to t minus 1. Note that these are the total demand that incurred during these periods will be the quantity that they are going to order. So I'm then going to have xjk. So again, this is the quantity that j is going to order. And then what I am doing is I am summing over all j's. Unfortunately, this n is also a random variable. Okay, so this sum is not a very straightforward sum. Now, how do we resolve issues like this? We take conditional probabilities, conditional expectations. So, for example, if you condition on a specific n, this is a simpler term. In other words, if you are given that n is 1, n is 2, n is 3, n is 4, n is 5, n is 0, this is a simpler term. And then you can actually find the probability of a certain n because you have it here. So it is going to be simple. So what we are going to do is we are going to compute expected value of this zt superscript ran. And in order to do that computation, what we are going to do is we are going to take the conditional expectation of the conditional expectation. So we are going to condition n to a certain value, find the expected value, and take the expected value over all n values this time. Okay? So for a given n, I'm going to take this expected value, and then I'm going to take the second expectation over the n values. Now this, I can sometimes, in order to simplify understanding, you can put a little n here, meaning that this expectation is going to be over the n values. Okay? Any problems with this statement? Okay. Now, of course, we need to write the same thing for the variance as well. And that is a little bit tricky because basically it is tricky. Why? If you recall from the case where we had stochastic lead time, the terms are not that simple to come up. But let me write in general what will be the variance of zt ran. The variance of zt ran is going to be the expected value of the variance of ZT ran given n. Okay, and then it will be the variance of the expected value of ZT ran given n. Okay, so what are these terms again? I am interested in the variance of this Z term, which has a random component in the sum. So when you have the random component in the sum, this becomes the expected value of the variance of the conditional variance of ZTN plus the variance of the conditional expectation of ZTN. Okay? So this variance is going to be taken over n values, and this expectation is going to be taken over n values. Note that when n is a constant, okay, what you are not going to have when n is a constant, you are not going to have this term coming into picture. In other words, there won't be any variance with different n's because there will be a single n, so the variance is going to be 0. Okay, now if you look at these terms, this is very similar to what we did when we had stochastic lead time. Remember, you can imagine this summation as this is demand during a single period, and this is demand during the lead time period. And if the lead time is stochastic, we had the same problem when we were trying to compute the expected value of demand during lead time. Okay, when lead time was stochastic. Remember, in the beginning of the semester, we did that. We actually derived this formula. Okay, so let me write this for you. This is sort of an exercise to show again, but we did that in the beginning of the semester when we were reviewing inventory. Okay. Now, given this, of course, we can apply this formula and simply obtain the variance. So when we apply the formula, then we are going to have variance of ZT ran is going to be equal to expected value of the, well, I don't need to write it again. It's right over there. But so now what is the variance of ZT ran given a certain n value? If I give you the n value, what will be variance of this term? It will be simply the variance of this summation. So let me write that. So this is going to be, well, I shouldn't do that actually. Given a certain value of n, you are going to have, all the demands are identical, independent. So here we have R demands. And then here we have n retailers. So in total, we are going to have n times R demands summed up. We are summing up the variance. So we are going to take the expected value over n, of course, but the variances are simply n times R times sigma square. Okay? Because we have sigma square is the variance of one demand. They are all independent, identically distributed. Then we are summing R of them here. And then here we have n of them, but n is a random variable, so that's the reason why we take an expectation. And then, of course, we are going to have the variance. Now I am going to take the expected value of ZT ran given n. And what is the expected value of ZT ran given n is simply, if you give me n, a single one has an expected value of m. The sum over all periods for R periods would be R times m. And I have an n here. So this is going to be simply n times m, or n times R times m. Now I can take the expected value and variance. Okay, so this is going to be R sigma square. What is the expected value of n? N divided by r, capital N divided by r. This is what we computed in the beginning. And then I am going to have r square, m square, and variance of n, which is n times 1 divided by r times 1 minus 1 divided by r. So if I rewrite this, this is n times sigma square, and then I'm going to have m square, r square, n, 1 divided by r minus 1 divided by r. Note that the r's are going to cancel, so I'm going to have n times sigma square plus m square. R's are going to cancel. Then I'm going to have n times r minus 1. Now, what is the value, what is n times sigma square? Now, so what I have found is, I have found the size, the variance of the orders that are given by this ordering scheme. Okay? So this is given by that. Now, what is the variance of demand per period? Now, this is each period you give an order, and these are the variances of the orders that the supplier is going to see. So I'm going to compare this with what? The variance of demand per period. What is the variance of demand per period? N times sigma square. We have an independent n retailers. Each of them is going to have an independent variance of sigma square. So I'm simply going to add that up. So actually this is the variance of demand per period. Okay? So you see that this is the variance of orders. This is the variance of demand. So you can see that this term is always going to be positive. It can be 0, of course. So you can see that the variance of the orders that you give is always larger than the variance of the demand. So what does this show? This shows that we actually see the bullwhip effect here. Now, when does the bullwhip effect cancels? If we order every period. Because what we are doing when we are ordering every period is that we are not letting the demand information be lost. Every time that we see the demand, we are giving an order. So if that's the case, then there is no information value. That has a lot of information value. Because we don't have any lead time here, we have nothing actually. Nothing that will complicate the system. So when r is equal to 1, you see that these two variances are going to be identical. Because we can see the demand as is, as in the supplier. On the other hand, if r is not equal to 1, you see that the terms that come into picture are not very nice looking because you have an m square here, which is the square of the expected demand in a given retailer, which might not be a small number. Okay, any questions on this? Okay, now you can see, of course, how the effect of the bullwhip effect is going to come into picture. Okay, now let's look at another case then. Okay, so the key here is if you can find that conditional expectation, the computation would be rather simple. Okay, now the second case, which is probably straightforward with respect to describing, I am going to have a positively correlated distribution, which is going to force the retailers to order more or less in the same period. So I do want to have an extreme distribution here. Make sure that I can represent what I mean. In reality, you don't expect retailers to order in a random fashion, of course. You expect them to order in a very correlated way. And it is going to be positively correlated. Because what happens is that they always have a scheme of ordering, and the operations are not different in two different retailers. So as demand increases towards the end of the week, they are always going to order for that demand. Okay, so this is basically what happens. So how are we going to represent this? We are going to write the following. We are going to have a distribution that will represent this idea. Okay, so what you do is you create a distribution which is going to represent this idea. So that distribution is as follows. We are going to have this probability equal to 1 minus 1 divided by r for I is equal to 0. Note that this is the case where no retailer orders. So probability that n is equal to 0 means that no retailer orders, and this is going to be the probability at any given day. It will be 1 over r, and this is the case when I is equal to n, and it will be 0 otherwise. So what does this distribution tells us? It tells the following. It tells that all the retailers are going to order at the same day, but that day is randomly selected. Okay? But they are all going to be ordering at the same day. So this is an extreme representation, of course, but we want to see the bullwhip effect in this extreme representation. But this extreme representation is closer to reality than the random case, because this is the behavior of the retailers, and we're going to do that after the break. Any questions?